Okay, so this is the second video for our mini unit on color of light, colorimetry, spectrophotometry, the nature of light. This is the second video in that mini flipped unit. We are going to pick up where we left off on the other one, but before we get there, I do just want to go back over what you learned in the other video. We said that light is part of what we call electromagnetic radiation, and that this electromagnetic radiation can be defined by the wavelengths of the different types of energy and the different types of light. We said that violet is the higher energy end of the visible spectrum, and that red is the lower energy end of the visible spectrum. And we talked about the fact that radio waves is at the lower end of energy, and gamma is at the higher end of energy, and that the wavelength and the frequency are also related to this. And the more energy that the electromagnetic radiation has, the more difficult tasks it can achieve, and the lower energy it has, or the less energy it has, the less effect it can have on motion of molecules, motion of electrons, and removal of electrons. We also said that we use C equals lambda nu and E equals H nu as our two main formulas for talking about wavelength, which is measured in meters, frequency, which is measured in cycles per second or seconds to the -1, and energy in joules per photon. Photons are what are given off or taken in when we're talking about releasing or absorbing the energy associated with light or electromagnetic radiation. And these formulas work very well together in concert with each other because of the fact that they each have frequency in them, which we abbreviate as the Greek letter nu. C stands for the speed of light, and H is Planck's constant. For those of you who are watching who are in AP chemistry, this is all found on the AP chemistry equations and constants sheet, and it is all under atomic structure. So for video 2, what we're going to be focusing on, we are going to be focusing on the energy of this electromagnetic radiation and what that energy is able to do. So if you follow along with me, my students oops, I went the wrong way. In your packet, you'll be able to see this is where we left off. We just did question number 3 at the end of video 1. So now to continue to talk about this nature of light, this is just another useful way to look at and break down the different wavelengths in meters. Again, in the other video, remember that we said visible light is going to be in the 400 to 700-ish nanometers range. And whenever we have around 700, that would be closer to the red, 400 would be closer to the violet. And here, gamma is on the higher energy side, and red, which goes all the way down to infrared, microwaves, radio waves, FM, and AM, we are on the lower energy side. So we can see that 10 to the 4 is a large wavelength, which correlates to lower energy, and this is a small wavelength, which correlates to higher energy. We also started to touch on energy and its relationship to light in the last video, so let's just talk about that a little bit. Max Planck postulated that can be gained or lost only in whole number multiples of h nu. And this is the idea that tells us that light and electromagnetic radiation act as both waves but also as particles. So the light is as acting as a wave, but at the same time, those waves correlate to the amount of energy per particle of light, which would be a single photon. This is that formula that we did at the end of the last video, and this has a little bit different because we said it was the energy per one photon if we don't put in the n there, but if we know how many photons, if we know how many photons, that's the n that we would multiply it by, because E is going to be per photon. If we multiply it by a number of photons, that would be the collective amount of energy for that number of photons. So we call this a quantum or a quanta, okay? And these are packets of energy. And the packet of energy is going to be that h nu. Every different frequency has a different amount of light in its packet, and it's multiplying Planck's constant times the frequency that gets us this amount. So the next question says that the blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees Celsius. And then this compound emits blue light having a wavelength of 450 nanometers. And they want to know what the increment of energy is that can be emitted by this wavelength of light. So for this question, they ask about the frequency and they ask about the energy. Now, it actually turns out that we need to find the frequency first because we are going to use C equals lambda nu to use the wavelength to find the frequency using the speed of light. Remember, these are all on the AP Chemistry equations and constants sheet under atomic structure. And then after we have our frequency, which is actually the answer to number 5, then we are going to plug it into E equals h nu using Planck's constant to find the energy per photon. Okay, so we are taking our 450 nanometers to do all of this. So I'm going to write down my given, which is that 450 nanometers equals my wavelength, which is represented by lambda. I'm going to convert that into meters, which means that I'm going to take out the n and change it to 10 to the minus 9. And when I put this into proper scientific notation, I get 4.5 times 10 to the minus 7 meters. I'm going to plug that in to the formula that has wavelength in it. Remember that lambda means wavelength. So I'm going to look on the formula sheet, make sure you have your calculator out. Write out what you think you need to put into the problem. And I'm going to write down my speed of light. And set that equal to my 4.50 times 10 to the minus 7 meters times x, because I'm looking for the frequency. When I divide both sides, my meters cancel, and I get x equals some number in seconds to the minus 1 for a unit. Remember, if you're plugging scientific notation into your calculator and it's a graphing calculator, you are going to plug in 2.998 second, comma, 8, and then your screen is going to look like this. If you are on a scientific calculator, you are going to do the same thing. It's still the button above the 7, only instead of second comma, this becomes second x to the minus 1, and you'll get the same thing on your screen. So now divided by 4.5 second comma negative 7, or 4.5 second x to the minus 1 negative 7 to get that EE button. Turns out that my frequency is 6.66 times 10 to the 14th seconds to the minus 1. That was actually the answer to the second question. Now I'm going to keep this unrounded value of my frequency, right? And I'm going to plug it into E equals H times nu, which is energy per photon Planck's constant and frequency. So basically, I'm going to take my frequency and multiply it by Planck's constant. Look for that on your formula sheet. So I'm going to take that number in my calculator, that is my nu, and I'm going to multiply by 6.626 times 10 to the negative 34. And I get my E value per photon of 4.41 times 10 to the negative 19 joules. That's per photon of this color of light. Now, I believe that is going to finish our second video. Yes, it is. So now at this point, you can try to do chapter 7, number 137, and see how you do. As always, if you had any trouble with anything in this video, you can always pause, rewind, rewatch. And of course, you are absolutely encouraged to speak to me in class or in extra help as well.